this week. So let's do a quick check. So, which state symbols would you use for the following in their standard state? So, this is some things we haven't necessarily referred to in this class yet, but standard state is a specific set of conditions, which is 25 degrees Celsius, so that's pretty close to room temperature, and 100 kilopascals of pressure. Um, so this is like the average atmospheric pressure, basically. So think of these things just as you would encounter them in everyday life, like at room temperature. And remember the state symbols. That's talking about the phase or the state of matter. So take a second, write down the state symbols for each of these things. Um, yeah, and their standard states. So under these conditions, I'll give you a second. So, number one, oxygen. That is in our atmosphere, right? We breathe it. It is a gas, so its state symbol would just be a G, right? Aluminum, that is a metal, and it is a solid at room temperature. Lots of cars have aluminum in them, or planes, so it would be S for solid. Water is a liquid, so its state symbol is L. Salt water, this would be AQ, which is aqueous, right? Because the salt is dissolved in the water. So we have a solution with water as our solvent. So we put that as aqueous. And then mercury is it is a liquid at room temperature. Yes, it is a metal, but it has a really low melting point, all right? So it is a liquid at room temperature, so it would be L. Okay, here's some more practice questions. Convert 25 degrees Celsius into Kelvin. Convert 300 Kelvin into degrees Celsius. Identify the state symbol for these substances in their standard state. Remember standard state under those conditions, 25 degrees Celsius, so about room temperature, and about 1 atmospheric pressure, or 100 kilopascals. Um, Take a second. These are questions you might see on IB test. See if you can figure these out. Okay, so the first one, we add 273.15. So if you do that addition, you get 298.15 Kelvin. If we're going the opposite direction, we subtract, right? So 300 minus 273.15, which would give us 26.85 degrees Celsius. So that's number two. For the state symbols, magnesium, and it is an alkali metal, and so it is a solid at room temperature, right? Nitrogen is the other big part of our atmosphere. Right? Our atmosphere is about 80% nitrogen, 20% oxygen, roughly. So nitrogen is a gas in standard state. Ethanol is a liquid. You might find this in certain types of gasoline. It's in alcoholic drinks, right? And then bromine water. That would mean bromine is dissolved in H2O. This is again the AQ, aqueous, because bromine is dissolved in the water. So, we have reached the end of 1.1. Good job. We are going to do a little bit of review together. And then I'm going to have you create something to help yourself review the feature. So remember, this is our guiding question. How do we model the particulate nature of matter? So we've seen a bunch of different representations of it. Those are all ways we can model it. But keep that in mind as we kind of look at all of these things. These are all kind of types of models that we can use. So here is a Venn diagram. Take a second, see if you can put these all into the right place. This was from our first lesson. So we have element, compound and mixture, right? Um, and then on the left, we have composed of only one type of atom, which would be A. B is pure. C is always contains chemical bonds. D is could contain diatomic molecules, and E is can be separated by physical methods. So some of these can fit into only one. Some of these can fit into multiple. So take a moment, see if you can fill this out, this Venn diagram, correctly. Okay, so here are the answers. A is an element, right, composed of only one type of atom. That is like the definition of an element. Um, B, pure substances can be elements or compounds as long as it's just the element or just the compound in the substance, right? C is a compound, right? Because if something always contains chemical bonds, it has to be a compound. Um, can't be a mixture or an element. Uh, D could contain diatomic molecules. This would be any of them, right? Because elements can be diatomic, compounds can be diatomic, and mixtures could contain them. And then E would be a mixture because compounds and elements cannot be separated by physical methods, only mixtures. And physical methods is like using the physical properties to separate things. So like all those separation techniques we learned the other day. So here's another Venn diagram. This one is solids, liquids, and gases. So see if you can fill this one in correctly. I will give you a moment to do that. Okay, so let's go through these. So the answers are right here. A is particles are in a fixed position. That is just solids, right? Solids have their particles in those lattices, which fixes them to each other. B, particles are in motion. That is all of them, right? All particles are always in motion, all states of matter. This is true. C, the substance has a fixed volume. This is true for solids and liquids, right? Gases fill whatever container they're in, so they do not have a fixed volume. D is the interparticle forces are negligible, and that is just gases, right? Gases are flying around. They are not really bonded to each other in any way, whereas solids and liquids are, which is why they both have a fixed volume. And then E, particles are close together. We would say this is solids and liquids. Gases are not. Okay, so here is a new thing we haven't looked at yet. But this is Johnstone's triangle. And you are going to fill it out for an ice cube. I'm going to explain what it is. And you're just going to do your best, but this is a way to think about different ways of modeling or representing a thing, in this case, an ice cube. So I'm going to come back to this graphic in a second, but Johnstone's triangle has three parts. The macroscopic, which is like macro means big. So macroscopic is the phenomena that you can observe directly. We are big. We observe the big phenomena, right? We can't see the tiny with our eyes. So examples would be like chemical changes in everyday life, cooking, rusting of metals, combustion, fire, right? Those are all things we see with our eyes, so they are macroscopic phenomena. Submicroscopic, so these are the things that are too small to see. So molecules, structures, geometry, polarity, the motion of those tiny particles, right? That's all smaller than we can see. So we call that submicroscopic. And then symbolic is like the ways that we communicate about the phenomena or the thing we're talking about. So we have a nice big periodic table which has a bunch of chemical symbols on it. That is a symbolic way to communicate. Formulas and equations. Like in math, we use these. Also in chemistry, we write chemical formulas. We've seen a bunch of diagrams in these slideshows, or like hazard warning symbols. Those are all symbolic ways to communicate about our objects and phenomena. So I'm going to give you an example, and then I'm going to go back to that triangle and have you fill it in. So, for example, if we are observing a reaction between a bromine solution and an alkene, and they separate, um, let's think about that. So, separating the macroscopic, submicroscopic, and symbolic out and then linking them together can improve long-term understanding. Like this is, I took this right from the Johnston Triangle website, but it's true. So for example, the levels in the reaction between bromine solution and hexene are, so these would be the three levels. Macroscopic, the bromine solution is quickly decolorized in the hexene. So we have the bromine solution here, and then as they react together, it changes color, right? We observe this. This is the macroscopic. The submicroscopic. So you need to know something about this reaction to say something about the submicroscopic, or at least know something about chemistry so you can make a guess. But what's happening here is the bromine molecules add across the double bond of the hexene to form a colorless product. So this is essentially describing what's happening on the tiny, tiny level. And the way that we can show that with symbols would be to write a chemical equation. So this is the bromine, right, Br2. This is the hexene, C6H12, and they are reacting chemically. So we have this arrow to create the dibromohexane, which is C6H12Br2. So this is an example of the three different levels, right? So I'm going to go back to this, right? And I want you to think about an ice cube, and I want you to describe it on the macroscopic, the submicroscopic, and then give it a symbolic representation. So pause the video, take a second to do that. Okay, so macroscopic, right? That's what you see, what you feel. So you could say, when I touch an ice cube, it feels very cold, right? That would be a macroscopic depiction. You could even draw a picture of it or take a picture. The submicroscopic, we could draw like a particle diagram, right? We've seen those for solids. You could just draw that and add an H2O for each of the particles, right? That would represent the ice cube. And then symbolic, you could write H2O with its state symbol S, right? That would be representing the ice cube. There are lots of ways to do each of these. So if you did something other than what I said, that does not mean it's wrong. You probably did great. But those are just examples of these three categories. So